Hi everybody, welcome back. We are ready for lesson 6.2, which is the dot product of vectors. So dot product, we're going to talk about what it is and why we are going to use it. All right, so let's get into what is the dot product. Well, the definition has been given to you. The dot product of two vectors is simply the product, a multiplication of the horizontal components and the product of the two vertical components. Notice we will then add those two numbers together. So all we're going to get out of a dot product is one number, and we're going to call that number a scalar number. It's not a vector anymore, it's now just simply one number. This dot product is also sometimes called the inner product, and so you might see that notation somewhere. It means the same thing. And one of the quickest things that we're going to use a dot product for is to find the length or a magnitude of a vector. There's a property here, and we will come back to that when we are ready to use it. And we're going to leave orthogonal vectors blank for just a second while we try the first example. So example 1, we've got three vectors A, B, and C, and we're ready to find a couple of dot products. So let's go with the first dot product. I'm going to do vector A times vector B, and all I need to do is multiply their horizontal components. 2 times 4 is 8. Their vertical components, negative 5 times 1 is negative 5, and if I take the sum, I get a 3. Simple as that. I found the dot product. Not using it for anything, just finding it right now. All right, second example, I want to try vector A times vector C. Alrighty, vector A is my same horizontal component of 2. Vector C is a horizontal component of 10. Multiply those two together, I'm going to get a 20. Vector A has a vertical component of negative 5, and C has a vertical component of 4. Obviously, negative 5 times 4 is negative 20, and notice we get a 0. Anytime when we are taking a dot product, we get a 0 product, we're going to find some orthogonal vectors. So you have a spot to write that. Orthogonal vectors will always have a product of 0. Let's see if we can see what's going on graphically, or what might be going on graphically. All right, vector A. Well, vector A starts at the origin, and it goes right to and down 5. That would be this vector right here, which is not the tool I was trying to use. Let's try that again. There we go. Now we have an arrow for a vector. Okay, so that would be vector A. Okay, how about vector B? Well, vector B will also start at the origin, and C. It will also start at the origin, and it's going to go right 10 and up 4. So there is vector C, and I'll note that for you right here. Okay, what does it look like is happening? Well, it kind of looks like those two vectors are perpendicular. Well, that brings up the point. It'd be awfully nice to be able to find an angle between two vectors rather quickly. We'll come back to that in just a moment. In the meantime, let's talk about that other property that's at the beginning of your page, and we're going to use the dot product to find length. Now, we've found length about 3 or 4 different ways so far, but we haven't done it with the dot product yet. So the property says that if I take the magnitude of vector u and I square it, that's the same as taking the dot product u times u. All right, double check I don't have Mr. Leckie here to double check me. Okay, so what does that mean? Well, if I'm taking the dot product of u times u, that means I'm going to take the horizontal component times itself, which would give me a 64. I'm going to add that to the vertical component times itself, which is going to give me a 225. That sum is going to be a 289. 289? Yes, indeed, 289. So what does that mean? Well, that means that I have the magnitude squared being 289. Obviously, the magnitude then would simply be the square root of 289, which is 17. The length of the vector is 17. Okay? You can double check that with the Pythagorean theorem if you needed to, or with a graph. All right, so back to this angle concept. The angle between any two non-zero vectors has a definition, and it's the corresponding angle between their respective vectors in standard position, meaning if I know their component form and I put them at the origin, same angle. Okay, I can pick up any vectors and put them at the origin. All right, the cosine of this angle, here's our definition. The cosine of that angle is going to equal the dot product of the two vectors divided by, fractions, the product of the magnitudes of those two vectors. Now, where on earth did somebody think up that? All right, let's take a look at a picture to see if we can figure out where this definition is coming from here. I'm going to start with a vector v. Just put it over there for fun. And I'll make a vector u going some other direction. Maybe this is vector u. And I kind of want to know what's the distance right here between these two vectors. Well, let me see what we can do. What if I subtracted my two vectors for fun? If I subtracted my two vectors, v looks a little longer, so we'll go v minus u. How would I do that visually? Well, visually, to subtract vector u is adding the opposite of vector u. So the opposite of vector u would be the same magnitude in the opposite direction. So there is negative u, if you will. And what if I then wanted to move this, because when I add vectors, I do tip to tail. It would be right about there. And you'll notice that vector v minus vector u is this green length. Just for fun, let's double check that green length. That's not how I do it. Double check that green length. There we go. And I want this piece. There it is. And it looks like those two are the same. Okay? So let me get him out of the way, and we're going to get him out of the way. And indeed, we've just shown you, just visually, a little quick visual check, that vector v minus vector u really is the green vector. Okay? So we're going to call this v minus u. Those are all vectors. All right, when I'm looking at this picture, I go, that's a triangle. What are all the tools and tricks that I know about a triangle? Well, I happen to know that if I know all three sides of a triangle, I can find any angle I want because I know the law of cosines. So let's say I'm looking for this angle between my two vectors. I'll call it theta. And if I want theta, and I'm going to use law of cosines, then I'm going to start with the side across from it, which would be the length of the side across from it, which is vector v minus vector u squared. Okay? And then I'm going to take that and set it equal to the length of the other two sides squared, because that's what the law of cosines says. So I need the length of v squared, and then I will need the length of u squared. Remember, if you put the absolute value bars, that means the length. Okay? And then I'm going to continue on with the rest of the law of cosines. So minus twice the length of vector v times the length of vector u, your symbols get a little tricky here, times the cosine of the angle in between, which remember was that green angle theta. Okay, so we've got a whole bunch of algebra to deal with. The first algebra I'm going to deal with is this right here. Well, that's like me, squaring something means writing it twice. And if I multiply out vector v minus vector u times vector v minus vector u. All right, so if I have anything being multiplied by itself, obviously I could take vector v times vector v minus twice vector u times vector v, right, plus vector u times vector u, okay? But the property that we just covered a second ago said that when I do this dot product, I'm going to get this out of my way here. There we go. I'm going to get the same thing as the magnitude squared. We just covered that. Okay, got minus twice vector v, that would be, times vector u. Get it together here. And then again, if I take vector u times vector u, we know that that's going to be the magnitude of vector u squared. Okay, just using that dot product property backwards again. All right, now we haven't changed anything on the right-hand side, so we can just recopy all that down. It's a whole lot of writing, so I'm just going to move it down. All right, meanwhile, we're ready to look at our equation here. What do we know about solving an equation? Well, I know that I have a vector u squared, the magnitude of the vector u squared, on both sides. And if I subtract them out, they will reduce to nothing. And the same thing with the magnitude of the vector v squared. But notice that my u's on my green side here and my u's on my black side. On the black side I have vectors that are magnitudes, and on the left side I don't have that. So I can't just cancel those. However, I am left with right now negative twice vector v times vector u equaling negative twice the magnitude of vector v times the magnitude of vector u times the cosine of the angle in between the two of them. And I can reduce both of those by negative 2. And now if I'm trying to find an angle, I would then get the cosine of the angle by itself, which means I'm going to have vector v dot product with vector u divided by, oh look, the magnitude of v times the magnitude of u. And if you read back up at the top, the cosine of the angle between the two vectors, which was right here, is the same thing as the dot product of the two vectors, okay, divided by the product of the magnitudes. And these would be the magnitudes, which would allow me to then find an angle. All right, so let's see if we can practice this. And by the way, this is what we're going to want to have to remember. All the rest of this was me developing where this came from, and it's simply using the law of cosines. So we just got to remember it's the dot product divided by the product of the magnitudes. And that's going to equal the cosine of the angles in between. So if we take u and v, we've sketched u and v. I've already done that for you. My u is my negative 5, 3 vector, and my v is my negative 4, 7 vector, which would be the blue vector. So here is v, and of course here is u. Okay? If I want the angle between these two, which would be right here, I don't have to figure out u and v separately and subtract them and all that good stuff. I can simply know that the cosine of the angle is going to be the dot product of the two vectors divided by the product of the magnitudes. Okay, which means I'm going to need some magnitudes. So let's talk about vector u. What's the magnitude of vector u? Well, that's simply negative 5 squared, which is 25, plus 3 squared, 25, and 9 would be 34. So we've got the square root of 34 for vector u. For vector v, we need its magnitude as well. And we're going to take negative 4 and square it, get 16, 7 square it, and get 49. Let's see, 16 and 49. Any other day of the week I could do that in my head is 65. All right, so we've got the product, we've got our two magnitudes. Now we just need our dot product, okay? So the cosine of the angle in between them is going to equal the dot product. That would be positive 20 plus 21 over the square root of 34 times the square root of 65. Okay, doing a little arithmetic, we're going to have a 41 divided by the square root. Since those are both under square roots, I can multiply them together and get 2210. And now I'm ready to do that the theta is the cosine inverse of that fraction, 41 over the square root of 2210. Type that into my calculator, and the angle between these two vectors is 29.291 degrees. Now visually, does that look like a 29-degree angle? Sure. Sure thing. Okay, now if we wanted to try that again for letter B, we've got two vectors. This time they're written as unit vectors, but remember this just means that vector A would be, oops, there we go, 2, negative 5, and vector C would be 10 and 4, like so. Okay, now those two vectors sound awfully familiar from a previous question, and in fact they are. If we do the dot product of these two vectors, let's see, we'd start with the cosine of theta equaling the dot product of the two vectors. That's going to give me 20 plus a negative 20 over their two magnitudes, but I don't even really care what their two magnitudes are because that's going to give me 0 on the top. Okay, what's the cosine? If the cosine of theta equals 0, what's my angle? Well, on the unit circle, the only time that the cosine is 0 is at 90 degrees or at 270 degrees. And if you graph these two, you'll see that means it's 90 degrees. So this takes us right back to the other example where we did our dot product and we got a 0. Notice we get a cosine of theta being theta 90 degrees. Cosine of 90 degrees is 0. And if you look back at picture on example 1, you'll see those two angles really are perpendicular. Okay? So orthogonal equals perpendicular equals an angle of 90 degrees. Okay, last topic, work. Besides doing dot products for angle between two vectors, which is a huge thing, okay, it's also helpful in physics to calculate what's called the amount of work that's needed to move an object from an initial point to a terminal point. Okay? In general, we want to remember that work is simply a force multiplied by a distance. Okay? Now, the directionality of the force is what becomes important. When F is a force whose direction is the same, I almost wrote parallel there, the same as the direction for the distance that the object is moving. Okay, then we're going to find force. Let's see, let me give you an example of that. Let's say that I have a box and I'm going to apply force F to it, and the box is sitting on the floor. Hopefully the floor is level, and the box is going to move this way. Okay, so the force is parallel. It is the same direction as the distance that the object is going to move. Okay, if that is the same, then all we're going to do is say that work is equal to force, the force vector, times from the initial point to the terminal point, the vector, the magnitude of the vector. Okay, so work equals force times the length that you are moving that object. Okay, what if force is in a different direction? Okay, what if I have maybe a ramp, okay, and I've got a box at the end of the ramp, but when I apply my force horizontally, the box doesn't actually move horizontally, something's in its way, and the box moves up the ramp. That's terrible. Okay, up the ramp. So in that case, obviously there's a difference between the direction of the force and the distance, the direction for the distance that the object is traveling. So we're going to need an angle between those two, okay? So when F is a force in a different or another or any other direction, okay, then work is going to be the force vector times, where did it go? Yep, the vector from A to B, the magnitude of that vector, times, again, the cosine of the angle between them. Okay? Now, if you happen to use the blue formula on a problem with the green formula, well, let's see, what's the angle going to be? The angle is going to be 0, and the cosine of 0 is simply 1. So it will still work. Okay? Couple of examples, and we will be on the road. Okay, example 4, find the work done when lifting an 87-pound weight. So this is going to be our force, and we're going to lift it 35 feet into the air. So this time they didn't give me an A and a B, but we know that the magnitude of AB is 35. Okay? So the work will simply be, again, the force is 87 pounds. We're going to multiply it by our 35 feet in the air, and we will get 3,045. Now what kind of units do we have? Well, force was measured in pounds, and 35 was measured in feet, so we're going to call these foot-pounds. It's one of the types of units for work. The other is Newton meters, and so you might hear that in a physics class. Okay, last example. What if I have a vector AB, and I'm given its unit vector form, rather, is 2i plus 3j, and the angle between the vector and the force is 30 degrees. Okay, so what's happening? Well, again, if my force is going this way, and from A to B, I have a 30-degree angle, okay, then I'm going to find work a little bit differently. I'm going to say that the work is going to equal the force, and the force is how hard I am pushing. I'm pushing 170 pounds, and I'm going to multiply that by the magnitude of AB. So how far is AB? Well, the magnitude of AB is simply the square root of 2 squared, the square root of 2 squared plus 3 squared, so 4 and 9 is 13, and we would have the square root of 13 times the cosine of the angle in between them. Now, since the cosine of 30 is 3 root 2, we know that, we could do this problem without a calculator and without making any messy rounding mistakes. Go like this. Well, 170 divided by 2 is going to be, I can't even do that today, 685, and this would be times the square root of 39. Let's try 39. Okay, now if you did have a calculator and you wanted to calculate that, just if you're following along, you could also write it as 530.825. In either case, again, we're going to call these foot-pounds because our measurement, oh goodness, there is an abbreviation for pounds, I really do know it. I'll just write it out. It's LBS, but I knew that. Okay, our measurement actually doesn't tell us that the object moving from A to B is in feet, but I believe the ones on the homework are, and we do have a pound force. Usually feet and pounds go together, and newtons and meters go together. Alrighty, I think that's going to do it for dot products. I'll see you in class.